In this section, we are going to be talking about the central limit theorem for means. This is a very big concept in statistics, and it can take a second to wrap your head around it, but once you do, you can see why it is so very, very important to us. To get started, we need to define a couple terms. The first is a sampling distribution. So a sampling distribution of sample means is a distribution that's obtained by using the means computed from multiple random samples of a specific size taken from a population. That is a very confusing sounding definition, and I find that the best way to explain or show you what a sampling distribution is to use an illustration that I have found online. So here we have a population. This one happens to be normally distributed to begin with, but we can technically start out with a uniform distribution or a skewed distribution of some sort, or we can create our own distribution, let's say. But what do we mean by a sampling distribution? So what a sampling distribution means is, let's say I'm going to take samples of size 5, this says. What that means, I'm going to animate it, is that I would take 5 random observations from my population, I would calculate up the mean of those 5 observations, and I have dropped down the mean of that sample. So I have one data value so far in my sampling distribution of means. And then I could do this over and over again. I could keep taking samples of size 5 and basically dropping down their mean. So I can do it again. Here's another random sample of size 5, and there's that mean for that sample. And do it over and over and over again, however many times that I want to do this. This distribution that gets created, these are distributions of sampling means, that's what we mean by our sampling distribution. So now I don't want to do this all day long. I don't want to animate it all day long. So what I'm going to do is just say, let's do this same process 10,000 times, drop down all those means all at once, and just show me what this looks like. This is my sampling distribution. Okay, so whenever I'm talking about a sampling distribution, this resulting graph of taking all these samples and calculating their means, so all of these values are sample means. That's what we've graphed down here. So that's what I'm referring to when I say that. So let's go back to here. Now that we know what a sampling distribution is, the standard error is what we call the standard deviation of the sampling distribution. So it's the standard deviation of that second graph that was being created. To calculate the standard error for sample means, we take the standard deviation of the original population and divide it by the square root of the sample size. So we can calculate those, and you will need to calculate those. This is a formula that you are going to need to know. It says, notice, the more observations you make, so that's this size, the larger n that you do, that means you're dividing by a larger value. And when you divide by a larger value, that actually ends up making the whole standard error smaller. So this goes along with what we've learned in the past, that larger samples allow us to be more precise. So I'm going to just go back to this example here. Notice that the standard deviation of this random population that I created was 6.56. But the standard deviation of my sampling distribution, this would be called the standard error. Notice it's 2.95. So what happened is, because I took samples of size 5, I was dividing this by the square root of 5, which is how I arrived down here. Okay, so it ends up making this, your sampling distribution, will end up having a smaller standard deviation than your original population. Okay, let's go back. So now we are ready to actually talk about the central limit theorem. What does this theorem tell us? So it tells us if you take a random sample of a population and your sample size is large and the population size is much larger than that sample size, then the sampling distribution of sample means, so this is all talking about that second graph. So what it's saying is if we do this correctly, if we take correct kinds of samples and drop down these sample means, that sampling distribution should be normal with mean mu, so the same mean as your population, and a standard deviation equal to the standard error. Okay, so let's see. Notes for this. It says a sample size of at least n equals 30 for us. This varies between books and sources. Sometimes they say 25, sometimes they say 30. For us, it's 30. Is required to assume that the distribution is going to end up close enough to normal to apply the central limit theorem. Be sure to check this condition before you continue. So if you're not taking samples of at least size 30, then you can't be guaranteed that this is actually going to work. If your CLT does not apply, then the normal distribution cannot be used to continue and find probabilities unless the original population was already known to be normal. If your CLT is not met, then the sampling distribution will still mimic the original population distribution, so then it may still be skewed symmetric or even bi or multimodal. And then another note is just on notation. A lot of times you'll see mu of x bar to denote the mean of the sampling distribution and sigma of x bar to denote the standard error of that sampling distribution. So again, let's go back to our image here. So what is the CLT telling us? It actually kind of worked out beautifully already. What it's saying is that no matter what this original population looks like, if we take enough samples of a good enough sample size, then this sampling distribution down here will end up being approximately normal. And look at what this sampling distribution looked like. I did it 10,000 times. Now my sample size was only 5, but I did it so many times that I ended up with a normal distribution. And also notice what the central limit theorem tells us. It says that this normal distribution should have the same mean as the original distribution. And look what we've got here. The mean of this sampling distribution is 16.46. And the mean of my original population is 16.46. Wow. And then it tells us how we should expect that the standard error down here is calculated. Okay, so how do we get from there to there? Well, we have a formula for that. Okay? And the beauty of the central limit theorem is that basically it's telling us that no matter what we start with, if we start with a skewed distribution, if we take samples of large enough, notice this one only lets me go to 25. But if we take samples that are large enough and we do it enough times, is 5 enough time? I only did this 5 times. That doesn't look normal. But if I did it if I did it 5 more times, well, there's 1 more time. It's got to do 25 of them here before it drops 1 down. So I'm going to wait for it to do that. Okay, there's my next one. We can do it 5 more times. It's starting to look a little bit more normal. 5 more, 5 more, 5 more, 5 more. The more that we do this, the more, quote, normal that sampling distribution starts to look. And if we do it a whole bunch of times, I just click the 100,000 times. Notice it also lets me fit a normal curve over this. And I can see now pretty clearly that that is very close to normal with the same or very close to the same mean as the original. And that standard deviation has been brought in by using that formula. The real magic here is that once we do this, once we have something that looks normal, then we're allowed to use the normal calculator in order to find probabilities.